charla. Bueno, la harás ahí al lado del laptop, ¿no?
Sí,
La cámara.
Sí, ahí estoy aquí. Vale. Anyway, thank you. Hi, good morning. We can start now. My name is Javi Garcia. I came from Spain. And today I want to talk about the high-level synthesis and what's the status of this kind of technology in respecting to free open source software tools. The point is that, as we will see, we have not a lot of alternatives to do this by using only free open source software. And the main topic or the main idea of this talk is to raise the flag about all the issues we have right now and to try to mobilize, to push the community in order to take all this issue. From our company, we have started to do some work in order to reach these kind of things, but as we will see, there is a lot of work to be done yet. Okay, let's start. I want to make some comments about the state of the art about high-level synthesis and why is this becoming very, very important right now. Maybe you are already aware of this, but in the last years, a lot of different algorithms are starting to gain a lot of traction, and that these algorithms require a lot of computational power. For example, we have embedded speech, we have embedded vision, deep and machine learning, big data, data mining. All of these kind of algorithms they are not very complex as per design, but they require a lot of computational power, a lot of math operation and extreme parallelism with the data. In this situation, the von Neumann CPUs, the well-known CPU, that used to be accelerated by the path of Moore's law is not scaling anymore. And we need to design or to develop alternative architectures in order to take all these kind of tasks. Well, this is where FPGAs come to the rescue. Most of these kind of tasks, these very computational intensive tasks, right now are taken by using GPU tools. For example, it's very well known the NVIDIA CUDA, so that you can program in a very high level, and they provide a lot of floating point parallelism, a very powerful, very powerful one. Sorry. The point is that, for example, this looks like very promising, but there are some algorithms in which this approach doesn't fit very well. For example, we have the inference in artificial vision that you might suppose that using floating points or arithmetic is a very good idea, but it's not a good idea. Empirical tests show that by using fixed point arithmetics, you might improve the most all of the metrics. You save silicon real estate because the logics, you need fewer logical gates in order to implement the thing. You also have fewer power consumption, and surprisingly enough, even the algorithm is more accurate by using fixed point arithmetics than using floating point arithmetic. This is maybe counterintuitive, but it's how the things really works. Some vendors and some hardware vendors, for example Google, are starting to develop their own very new hardware architectures, but if you develop a chip from the ground up, the costs are very, very high. So in this kind of algorithms where you can change the algorithm, the software is constantly evolving, flexibility is a must. And this is where FPGAs came to the rescue, because per definition you cannot find any more flexible than an FPGA. And the thing is that the whole industry is looking at FPGAs for answers. Let's see some examples. For example, we have the Wintel is striking back. Wintel is Microsoft plus Intel is where we used to call that. And it's striking back. I don't know if you were aware of this, but Intel has just bought Altera. This was the second brand of FPGAs in market share. And it was funny enough that a couple of years ago, in the first EDA dev room, in the digital design panel, we started to talk about a rumor about Microsoft getting involved in FPGAs and so on, and about Project Catapult. That is an SDK that Microsoft has just released in order to accelerate software by using FPGAs. They are partnering in some way with Intel, and for example, they are already using this in the Bing search engine, and they are planning to use this also in Office 365. In this picture, I really like it. Do you have a Xeon processor in which in the same package we have the multi-core CPU and an Altira FPGA all packaged in the same socket. So this kind of technology is going to be pushed in the data center a lot of, but not only the consortium formed by Intel and Microsoft is using this approach. There are some other examples too. For example, we have Baidu, I don't know how it's pronounced, that is accelerating SQL at the data center by using Xilinx Kintex ultra-scale parts. I don't know if you were aware of this, but it's very interesting. As Philip has said before, Amazon Web Services are already offering some units in which you can accelerate the software by using up to 8 Xilinx FPGAs. And IBM, and with this intelligence augment concept, started to work with Xilinx and in order to integrate their PowerPC CPUs with the FPGAs coming from Xilinx. And even more, they have designed their own chip for deep learning that is called True North. And what is not more people know that this chip is actually designed by the Cornell University FPGA experts. So what is really in this chip is a very specific FPGA. So after these examples, let's focus on how high-level synthesis works. Well, the target is to accelerate software algorithms by using an FPGA. What does this mean? Okay, we want to automatically generate a code for a high-level definition. For example, OpenCL, the language that is used in CUDA, the language that is using for NVIDIA and other hardware platforms for acceleration, is becoming the de facto standard for most of the FPGA vendors too, namely Xilinx or Intel, formerly Altira. The idea is to take all this growing community of GPU-based programmers that are very used to use OpenCL and this kind of technology, and take them and provide FPGA tools in order to allow them to program an FPGA without noting that they are using an FPGA. These are very complex and expensive commercial tools in which you provide an application, the application gets profiled by a Valgrind machine or something similar, and the most computing-intensive tasks are identified, and there is an automatically generation of the FPGA code that cover these parts of the software that is most intensive. Then the software part is compiled, and the hardware part, the gateware part, the part that is going to be deployed in the FPGA, is also compiled and generated. And then another piece of these tools is a special kernel module that is in charge of loading and unloading the FPGA's cores as they are demanded by the algorithms. How are we approaching this kind of stuff from our company? Because in the past there have been some tries to develop a high-level synthesis tool in which you can program almost anything, and it gets automatically profiled like in the tools that the FPGA vendors are providing, but it's very complex. There is actually there is not any free open source tool that is working right now in this way. So our idea is to provide a set of hardware-accelerated libraries for a specific purpose. Let's see. For example, if we are going to program digital signal processing, we want to have a set of libraries in which the most common operations are already pre-synthesized, so that you can use the call a function, and what you are on the thing, what this is doing is taking this pre-synthesized thing. This also has application for other libraries such as embedded vision, inverse kinematics, and so on. The provided libraries must include a software side providing a wrapper, like an API in order to link with the standard software so that you can program a standard program and call these kind of libraries, and a gateway side, the FPGA side, in which the optimized HDL code is already pre-synthesized. This must be transparent for the programmers so that they can just use the API, make some includes, and use this function. And the system, as in the previous case, needs to be in charge of loading and unloading the FPGA part as the code, as the binary that you are executing, the program in the CPU is needing the FPGA part in order to accelerate the thing. How do we can integrate the FPGA into the operating system in order to get this kind of thing? Okay, for sure, first of all, we are only focused on Linux. I am not going to talk about Windows or nothing at all. And what we need, as I have previously said, is to have some hardware-accelerated libraries with their own associated bit stream for the FPGA. We need to know that different library versions, talking about libraries in the standard software, point of view, might require different bit stream versions too. So we need to match the software part and the bit stream part. So what we are doing is to package in the associated bit stream for each of these libraries as a Linux package, so that we can establish interdependencies between the FPGA part and the software part, so that if you need to install a software by instance of this kind of libraries, the bit stream is also deployed and the version matches the version of the software library too. And it's very important also, there's a comment that the bit stream needs to be pre-synthesized. And why this is also important? Well, because synthesizing a bit stream is a very time-consuming task. You can lose a lot of time. You cannot be synthesizing on the fly. And even more important, because only x86 processors are able to run the most of the synthesized tools that are available today. Maybe Yoshi is an exception, but we can talk later about this, because if you are using an ARM processor, you cannot synthesize the thing inside the chip. We are using Yocto project as the building system, so that everything, including the bit stream or the different bit stream associated to the libraries, are managed. And we use HDL-make in order to integrate the bit stream synthesis inside the system, the operating system generation, so that by using HDL-make, we can generate some recipes in which we specify Yocto project, the building system, how it needs to handle the HDL code in order to generate the package including the bit stream. As a couple of examples, we have used this with the CERN Open Hardware Kit in order to provide, just for internal use, by the way, by the moment, to provide the automatic support for all different modules, different hardware that can be inserted in a carrier board. Sorry, I have not explained this because I think I'm running a little bit out of time. This board is a board in which you can plug different hardware modules, and each of them have different functionality. These are controlled by an FPGA, and depending on the depending on the module you are plugging into, you will need a different bit stream on the FPGA too. So by using HDL-make, we have generated different packages, different Linux packages for each of these different modules that not only include the the kernel module, but we have also package for the user-spy program and also for the FPGA, so that if we want to make a Linux runtime in which one of these modules needs to be supported, by just installing one of the packages, all of the different ones are generated and installed. The user space program, the kernel module, plus the FPGA system. Another very interesting example that we are using is for robotic controls. I don't know if you have heard about ROS, the robotic operating system. That there is one of the parts of this project that is called ROS Industrial, that is devoted to applying robotic operating system to industrial manipulators. And it's also a free open source SDK. In this kind of robotic controls, there is a need for massive computational power. We are part of this consortium, and we are in charge of trying to accelerate the most intensive algorithms that these robots use by using FPGAs. And for example, the most appropriate examples in order to do this is the inverse kinematics. That is, as you know, you take a robotic arm, tell it where you need to put the tooltip, and it automatically calculates all of the movements or the different servos it has. It has a very computing-intensive task, and in order to planify a path or a movement, a robot might lose about tens of seconds. Tens of seconds. Maybe even a minute is complex enough. Another one is point cloud, that is more related to artificial vision and so on. Yeah, artificial vision and so on. And we are working in applying the previous approach to this kind of to these two examples. We have a missing feature that need to get into the FPGAs in order to be able to use this approach of having library accelerated by FPGAs. That is the partial reconfiguration. Maybe of you have already heard about the Pareto rule that applies to libraries in general, so that not all the libraries are used at the same time. And most of the libraries are in the processors are unloaded in the cache memory as they are required. In order to perform or to implement this approach in an efficient way in FPGA, in order to accelerate libraries in an FPGA in an efficient way, we need a way in order to reprogram only slices of the FPGA, not all the FPGA. We need to handle the FPGA configuration memory just as the CPU handle the cache memory. There are already some tools that are able to do this, but they are but they are very expensive and they are not commercial alternatives. And they are only supported in higher-end devices, and well, they are very expensive. And some conclusions. There are not a lot of FLOSS, free, libre, open source tools in order to do this. HDL-make is a very interesting tool that allows us to at least to manage all the pain of handling FPGA and libraries together. And we need also an HDL library standard. Maybe IP-exact can be a good candidate. We need maybe another alternatives, and it's very important also to have a IP integrator, and maybe FuseSock can be a very good idea in order to use in order to do these kind of things. And finally, to have a workaround for partial reconfiguration. And that's it. Sorry.
No, you had a video, right?
Yes, but I am running out of time.
Yeah, it was
marking your minutes without the video.
Okay. I have told you before. I have told before about the HDL Make. I am the maintainer of HDL Make. I have told you about high-level synthesis, but this is my core tool, and this is an assistant to a command line tool in order to make the life easier for FPGA designers. I have some stuff, but I want to show you a video about about the brand new graphical user interface I am developing for HDL Make. Let's see. Sorry. Oh. Okay, can you see that? I am in this video. I am just going to create to clone an HDL Make project taken from the Open Hardware repository, a site maintained by CERN. Once I have already downloaded this repository, because HDL Make is very useful in order to use a control version for your HDL code. I have already now loaded the Silence ISE tools, and then I am going to launch the HDL, what right now I call the HDL Maker. It's like a Node JavaScript wrapper for HDL Make, so that you can open it in a web page, so that you can run the synthesis even in your own computer and open this graphical user interface, or even run it in a server with all the tools installed and just accessing with any other computer. We have some different controls. Now I am fetching the code because it automatically fetches the libraries it needs, the IP core libraries it needs in order to make the synthesis. And as now I can make a pause because synthesis process is very, very time consuming, a very time consuming task. And now here we have running we can see that the synthesis is running, well, the fetch is running, and now I am going to make the auto, so that a synthesis makefile has been just generated. Synthesis makefile generated, and now I am going to run the make command, because HDL Make produce makefiles. We are running in local mode, and then all the ISE stuff from Silence start appearing in the screen. Now we need to stop, because this is very time consuming. And after some minutes, we're going to be faster right now, the synthesis has finally ended. Okay, maybe that video is not. Okay, the synthesis has finally. Oh, I thought the video was shorter, sorry. Okay, now we have a programming file. We have already generated the bit stream, and then we could go to a file browser and to grab the bit stream and to download it. This is very useful if you are running the synthesis in a different machine, so that you can access through your web browser, and the synthesis is performed in another big machine, and you can just grab the bit stream. And one of the cool things we can do with this, maybe this is the most interesting one, is that when you have already parsed the design and you have the relation between the inner parts of the design itself, we have added a project navigator, so that you can see the whole structure of the design itself. You can browse the design. You can close and collapse and expand the different branches from the design. I think there is not many more to explain in this. Well, we see that we can zoom and to navigate, and we can collapse the different branches also, in order to focus in the parts of the design we really want to focus on. And I think the video is, yes, it's a minute left, but it's the same. I did not move from from the browser.